So the question today is the discussion board, and that's good because I saw a few mistakes when I was grading the discussion board. So let me bring it up here really quick. Wrong class. So the discussion board today is the idea of electroplating and the idea of basically how much material reacts. So the problem itself, 2Fe2O3 solid plus 6 electrons goes to 4 iron atoms plus 3 oxygen molecules. And the question is, if we pass 1.33 amps for 1 hour, we want to know how many grams of iron are plated out. So the thing to keep in mind with these problems, before we solve this, let's talk conceptually about what's going on. Electrochemistry, batteries, are actually really nice for understanding how reaction kinetics work because we know we can measure amp. We can measure the number of electrons flowing through a wire. And because of that, voltage is a direct measure of the extent of reaction, how far the reaction has gone. So in the online notes, and you'll find this on slide 94, there is a formula, I, the current, times the time, times 1.037 times 10 to the negative 5 times whatever we're interested in by the number of electrons times the molecular weight equals the grams plated. So here's the thing. All this formula is really saying that our current is related to our X, our extent of reaction. So if we know how far the reaction went, we can figure out how much metal was plated out. Now this time here has to be in seconds. And the reason is that amps are a coulomb per second. This 1.037, 10 to the negative 5, these are all just conversion factors. And if you go to the online notes, you're going to see it worked out a lot better as to where this 1.037 times to the negative 5 comes from. But basically, when we get to this point, we are in moles of electrons. So current times time will give us electrons, but it'll give us literally electrons. And this 1.037 times 10 to the negative 5 gives us total number of electrons, total moles of electrons that have been used in this reaction. The coefficient here is whatever we're interested in. So if we were interested in Fe2O3, we would put 2 here. Since we're interested in iron, we're going to put a 4 here. Now the challenge with this, and I did see this mistake made on a few of the solutions that were submitted, this new here is not the number of electrons corresponding to the iron oxidation state change, because here we have iron plus 3, and here it goes to a 0. You're going to use the coefficient directly in the problem. So this half reaction here, the 6 goes down here. And at this point, you're in moles of whatever you're interested in this case, iron. So your molecular weight here, I think is 55.6 grams per mole. That's just a unit conversion. So to solve any of these types of problems, it's basically this formula, which you'll be given on the final exam, you figuring out what variable is missing and just kind of having to accept that this thing here is converting all your units. So it's getting them to the point that we're working in moles of electrons. But in terms of other problems, if you want to work one, there's several on the practice packets. And I think it works out to be about 1.85 grams on this particular discussion board. So do let me know if you want to work one, and then I can bring up an example on the practice packets that's online, and we can work through that. It's 15-second lag. For difficulty's sake, would you make us convert various pieces to the correct factors for the equation? Really, the hardest I ever make these problems and the hardest they ever actually get is asking you to solve something on the left side. So if I say, and we can work an example of this from the packets, how long does it have to plate? What current did I have to use? But generally speaking, I would give you a balanced redox reaction. The reason being is that if you're wrong here, you're going to be wrong down here, and it's just too many concepts trying to be juggled at once. I try to limit to 2 to 3 concepts at the same time. So let's look at one of the more hard problems. Do I actually have one? Oh, geez, no. So if you go to the practice packets, and I'll bring it up really quick so you can see it. I'm still trying to figure out how to make this program actually like go to a particular window. So we'll work the last problem on page 10 here. If a battery produces 0.133 amps of power for 2 hours and how much iron was consumed at the anode reaction is Fe plus 2 plus copper goes to Fe plus 4 and 2 Cu. So I'll give you a minute to write that down. Well, I'll give myself a minute to write this down. So we have iron solid plus 2 copper plus 2 goes to Fe plus 4 plus 2 copper. And we've got 1.33 amps, 0.133 amps, and there is a reason for working with that number. For 2 hours. And we want to know how much iron was consumed by the reaction. There you are. So, how do we solve this? Well, we've got our formula. Current times time times 1.037 times 10 to the negative 5 times the coefficient on what we're interested in. In this case, we're interested in iron, divided by the number of electrons which are transferred times molecular weight gives us the grams of Fe. So this is the formula we're going to work with. Again, you're going to be given this formula in the final exam, so you don't have to worry about memorizing it. You've got 0.133 amps. The only hard part about this particular problem is that you're given 2 hours. Your time here has to be in units of seconds because of the units on amperes, which is a coulomb per second. So that's going to be 7,200 seconds times 1.037 times 10 to the negative 5. Your coefficient on iron from the problem is 1. The number of electrons transferred, it doesn't matter if you work with the oxidation reaction or the reduction reaction because this is a balanced redox problem. And again, I'm not going to give you anything that's unbalanced. That's too many complications. We can now look at the iron, which goes from 0 to plus 4, which is 4 electrons, or we can look at the copper, where it goes from 0 to plus 2, but there are 2 copper atoms doing it, so it still gives us the 4 electrons, and we've got our 55.6 grams per mole. So if we multiply those out, the 0.113 times 7,200 times this number times 1 over 4 times 55.6, this will give us the grams of iron that were consumed by the reaction. If we instead wanted to know the grams of copper that were produced, so let's say we want to go to Cu here, we would change this number to 2, and this to whatever the molecular weight of copper is. That's one of the few I don't actually know off the top of my head. But honestly, that's as hard as these problems get. The derivation of this formula, if we were having a CETA class, we'd work through how this derivation comes about. I think there's actually a YouTube video where I show how this comes about. It's basically just unit conversions. That's all it is. So hopefully you kind of see this as a very lightweight problem. Bigger challenge, and again, this problem really represents the hard end of the spectrum. Determining the number of electrons from a balanced redox reaction, assuming you're not given a half reaction, which explicitly states it, and converting to units of seconds. So you got 0.138 grams. Let's see what the key had to say. So give me just a minute. And these solutions are available on the course website. If we were in a CETA course, I wouldn't let you see these, but It doesn't matter if you camp out in the classroom with the key now. Yeah, I get 1.39 grams. I'm guessing that's just more rounding than anything else. So the 0.138 grams is correct. Plan for next week, specifically for the lab or for the class itself? So yeah, these problems for plating are simple. Just remember to convert your units. The videos on question 13 on the Nernst equation lab don't work. So are they my YouTube videos or are they the ones that are the alternative assignments? As far as starting to go over the final exam, next Monday is technically allocated for any questions you have on nuclear chemistry. That said, I think most of you are going to find nuclear chemistry is pretty trivial. So pretty much any day next week, Monday or Wednesday, if you want to start reviewing for the final exam, that's perfectly fine. Ask me any questions. There is that big fat packet online that's the review for the final exam. Well, we can also, we're definitely going to talk Wednesday about the topics that are going to be on the final exam. Your final exam is 35 multiple choice questions. The distractors are achievable, which means that there's going to be partial credit associated with certain distractor answers. But the other reason I'm giving the multiple choice is that because Friday, the last day of exams, we turn around Monday and we start the summer courses, I have to have my grades in like Monday at 8 a.m. So the multiple choice, while it's unfortunate for you, does kind of expedite the grading and gets me in before the deadline. So again, the reason we're not going to work, I will probably provide you, probably not even going to provide you with the link for showing your work. The big reason is that these are what are called engineered distractors. The only way you can get them is if you did your work a certain way. And because of that, that's why you're getting the partial credit. Now, that said, I'm going to try to stay on top of the final exam material. So if you take your final exam like Monday or Tuesday, I can get all your grades up. And if you say like, oh, I'm like a point away from this, then we can start talking about maybe going back and regrading a few things. Make a video. I'm not a huge fan of multiple choice questions. You're going to find that a lot of good professors are against multiple choice because for this very reason, they don't show me where you're not understanding. You may pick a distractor because you are randomly picking answers. You may pick a distractor because you actually understood it and that's where you got to. This is just kind of the nature of the beast. So with the final exam in general, typically what we do with the final exam every year is we do multiple choice. And again, it's just for rapid grading purposes. Again, take it early. I'll try to keep on top of your grades, post them so this way you can see what you have in the course. If you take your final exam at like Friday at 3 o'clock in the afternoon, you finish Friday at 4:50 and say, hey, I want to talk about my grade, there's not much I can do for you because your grades are like literally due that weekend. So there's not much we can do in terms of negotiations. But if you do something Tuesday and you say, hey, I'm not happy with my grade in the class, we might be able to talk about something, particularly if I have time to go over how you performed in the course. But again, if you're going to wait until like Friday at 3 o'clock, because I think 3 o'clock is when it's going to cut you off. Fun fact about Blackboard, by the way. So you get an hour and 50 minutes for the final exam. The cutoff is 5 p.m. Friday. If you try to start your exam at 3:11 in the afternoon on Friday, it will not let you take the exam. And the reason being is that Blackboard will not let you in if you don't have that time window to take it. So at 3 o'clock, 3:10 in the afternoon, Friday afternoon, Blackboard is going to sit back and say you don't have enough time to have the full hour and 50 minutes, so it's just automatically not going to let you have it. You have from Monday at midnight, first thing in the morning, until Friday at 3:10 in the afternoon to take it. Please don't be that student that takes it 3:10 in the afternoon, because again, I have to get the grades in, and I can't submit the grades a la carte to the school. I have to submit all your grades at once. So again, take it early. If not for my sake, then for your sake. If you take the final and you just like don't do as great as you thought you should, then I can go through your exam with you and say, okay, because maybe there may actually be legitimate grading issues. I'm not going to have the time to look through all 35 questions if you send me an email at Friday at like 6 o'clock in the evening. Like, there's just not much I can do for you at that point. So, the makeup lab video A and B say they're removed on YouTube. Let me see if I can hunt those videos down for you really quick. So for the nurse lab, I'm seeing everything is there. Now this is one section. Let me make sure this isn't an issue with the other section, because my courses aren't merged. So I'm not seeing any videos underneath the lab tab. So Abby just asked about the exam, the 11th through the 15th. Yes. So I'm going to give you Monday midnight. If at 12:01 you decide you want to take the exam Monday morning, power to you. It's available. You get the full 5 days plus before the start of business day on Monday. Some instructors will be opening their exams up on Sundays. I think that 5-day window is more than reasonable, especially since you get to take it at your leisure. So you have the full 5 days of exams. You're going to find out from your instructors. I know there are some instructors that are setting their exams to 2-day windows, so I want you to have that flexibility that if they say, oh, you have to take it Tuesday and Wednesday, which is to show you how instructors think. So many instructors proposed at the last meeting that they were going to set their exams Tuesday and Wednesday. Okay, I guarantee you every other instructor you had the exact same idea. So I don't want to be that professor. I want to give you the full 5 days, and if you have exams Monday and Tuesday, that gives you either Monday to take mine or Thursday to take mine, or if you really want to rest on Thursday, it'll give you Friday to take mine. The lab document. Oh, I think I know what you're talking about now. Hold on. Oh, that is good to know, Camille. Thank you for letting me know. So, for now, skip that last problem. And I'll try to send out an announcement about that after I get done with our discussion today. This is from the PhET website. We're relying on them heavily for the labs because they already have the simulations done. Like most organizations, they probably made this document a few years ago and completely forgot they had it. So since this is just the last problem, question 13, I would say just skip it. It's not worth hunting down the PhET people to figure out what's actually going on. So yeah, I'll just give you question 13 for free. Hey, thanks, Camille, for starting the lab in a timely fashion. Let's see what else was on the nuke stuff, or the electrochem stuff. Oh, not much. When I first started teaching Chem 2, I actually had the electrochem stuff broken up into and the nuke stuff on 2 separate packets. So you would get like this little 2-sheet of paper for the nuke, and I'd say like, this is all you gotta learn. Whereas electrochem was a little bit meatier. But particularly with coming off test 4 where you were used to the booklet packets, it was a nice refresher when students got to see like these really thin packets. Sure, we can go over decay pathways. So in the final exam material on the course website, there's a table. And I'll flip it over for you to see really quick. So we've got, let's see here, 6 decay pathways. The alpha decay, beta decay, proton, positron, gamma ray, and neutron. And hopefully I haven't run the neutron too far down on my board. See it? Yeah, you can see neutron. So the pathways themselves, an alpha decay is when you lose a helium nucleus. So if we have a molecule doing alpha capture, it happens, it's rare. Typically this is seen with nitrogen and oxygen. Nitrogen will capture alpha decay to give you oxygen. Typically there's something like uranium decaying into thorium. That's what you see happening. So uranium 238 will decay into thorium 234. by an alpha decay. Now, the weird thing is that when we do nuclear decay, we don't write charges. I do. You're not responsible for it. It just really annoys me because this historically was important. It's ejecting a helium nucleus, an He plus 2. Now, it does acquire 2 electrons from the atom when it ejects, but the big thing is alpha particles are deflected by magnets because they have a positive charge. Second pathway, beta decay, is really an electron. And the way we write the electron is that it has a -1 charge and a 0 mass. Now, electrons really aren't 0, but relative to the mass of a proton or a nucleus, it's effectively 0. So when we have beta decay, it comes about from a neutron decaying into a proton and an electron. Now with beta capture, we have the reverse. So if a beta particle is absorbed, very rare, but if it does absorb, it reacts with a proton in the nucleus to give us a neutron. So when we have beta decay, what's happening is that we are converting a neutron in the nucleus to a proton by ejecting an electron. So simple example of this, sorry, we have, let's say oxygen 20. And we do beta decay, so we'll get oxygen 19. Why doesn't that look right? Oh, because I've got the charge in the wrong place. Sorry, been a while. The -1 actually goes down there. The mass is on top, charge is on bottom. So we get this decay. So when we have beta decay, basically we're increasing the atomic number, which we're creating the next element to the right in the periodic table. Proton ejection, which is pretty much all you're going to see, is just when a nucleus ejects its proton. So let's say we did the reverse. We have F19 and we eject a proton. We would get oxygen 18 plus the proton. And as you expect, the proton has a +1 charge. Proton decay, I'm not as familiar with. I don't think it happens that much, but it does occur. The big thing is that you have the wrong ratio of neutrons to protons. So you're trying to get that neutron ratio up by ejecting a proton. Now, positrons are weird. So a positron, I wrote it wrong, occurs when you have a proton decaying into a neutron. Oops, put it wrong. So a positron happens when a proton decays into a neutron. And you may sit back and say, well, won't you make a proton, don't you create a neutron by adding a proton-neutron? Nuclear chemistry is weird. So when we eject a positron is antimatter. So if we have a positron, E plus 1, plus an electron, still keep writing in the wrong place. They annihilate. So a positron plus an electron annihilate to give us gamma rays. We'll get back to what a gamma ray is. Neutron is what you expect. You have a neutron in the nucleus, you get rid of one. Actually, the reverse is far more common, and this is in kind of a side effect of when we do neutron diffraction with materials. So if we have something like carbon 12, and we have a neutron, we get carbon 13. So this is a big issue with neutron diffraction and neutron spectroscopy, is that materials will absorb the neutrons. Sometimes the case is something like carbon 13 that absorbs a neutron. It's a stable isotope, no one cares. Sometimes it absorbs a neutron and the isotope it creates is highly unstable and we get radioactive decay. But neutron capture is the far more common one you're going to see. This is also what gives rise to things like fission and fusion. Now the gamma ray, a bit hard to explain, but it's actually a concept you're kind of familiar with. So to understand gamma rays, let's go back to electrons. And if we look at electrons, So heading back to Chem 251, you got 1s, 2s, 2p, 3s, 3p. So again, we're going to focus on electrons here. So if we have electrons in excited states, so let's say we had, if this is carbon, a neutral carbon atom, we can excite it, sorry, not plus, asterisk. We can excite it by hitting it with a bunch of energy. And what will happen is that when it decays, when it releases that high energy electron, it will emit a photon of light. And so electrons lose energy by emitting a photon light. Now, nuclei are very similar, and this is something I really criticize your book for because they stay away from this topic, even though it's not that hard to explain. Inside the nucleus, we have nuclear atomic orbitals. So for electrons, these are electron orbitals. Nuclei are the same way. The protons and neutrons have their own energy states. Two big problems here is that, one, we can't produce the energy necessary to probe them. So electronic transitions we can do with fire, we can do with visible light. With nuclear spectroscopy, you need gamma rays, and we cannot domestically produce gamma rays. We can watch them be formed, but we personally cannot produce them. So what happens in gamma decay? So let's say we have uranium-238, and it decays into thorium. And it does it by alpha decay. Well, this is really a gross oversimplification because what we create is an excited thorium nucleus. And this is going to have high nuclear spin. So if we were to build a hypothetical, because we don't actually know what the actual nuclear atomic orbitals are, the hypothetical thorium here would look something like this. We have a whole bunch of unpaired neutrons and protons. They each have their spin 1/2. What will happen is that this this thorium-234 will emit a gamma ray. And what this gamma ray reflects are protons and neutrons dropping down in energy within the nucleus. And doing so creates a low spin nucleus. So what gamma rays, even though it doesn't look like, because we show the gamma but we don't say what it is protons and neutrons pairing up in the nucleus to reduce their spins. So combining their spins. So electrons have a spin up, spin down. We're in the same atomic orbitals, their spins cancel. The same thing's true of protons and neutrons. When we see this gamma ray decay, what we're seeing is a reduction in the actual spin of the nucleus itself. Because what happens is that when we have the other decay pathways, we change the energy of the atomic orbital, the nuclear energy orbital, nuclear orbitals. They have to relax down to a lower spin state because they want to go down in energy, much like an excited electron wants to drop to a lower energy orbital. Same thing's going to happen here. So yeah, I realize this is really kind of in depth because gamma almost like never gets discussed with nuclear decay. But it really annoys me that like books just kind of gloss over like, gamma decay is there. Well, what does it do? It decreases the spin of the nucleus. And it's decreasing the spin of the nucleus because the protons and neutrons are dropping down in energy within the nuclear energy levels. They're pairing up, that reduces spin and releases energy. So those are your 6 most common decay pathways. Is that more than you ever wanted to know about nuclear decay? So the example I love to give in class when I'm actually able to teach this course in class is I give you the example. Let's say I have two pocket watches and they are identical down to the atom. So somehow I managed to take the same watch and clone it so they're exactly the same, but I'm going to wind one up. Who weighs more, the wound up watch or the unwound watch? And let's see what y'all get back in the comment section. Which watch would weigh more? So yes, you're going to have to be able to determine which decay pathway is being used. Particularly in the final exam, it's going to say like which decay pathway does this correspond to. The nice thing is that all the decay pathways have a unique symbol. So for alpha, it's a helium with a 4-2. With beta, it's an electron. With neutron, it's a neutron. With proton decay, it's a proton. With a positron, it's the electron with a +1. Gamma is going to be the only one you don't actually have to identify. It's present in basically all nuclear reactions. And with this example, we'll talk about how it changes the mass of the nucleus, but it's such an esoteric thing, most books just kind of stay away from it. But yeah, what weighs more, a wound or an unwound watch? They don't weigh the same, actually. Now, on the lab scale, you can't practically weigh the difference, but they do actually weigh different things. This is actually the easy proof of Einstein's relativity theory. General relativity, not special relativity. There you go, it's potential energy. So we have the relationship E equals mc squared, but let's turn it around. So let's say for the moment that, so this is true, mc squared. So E equals, we have two types of energy here. We have the rest mass, and we have the potential energy. So E here equals, actually this is kind of misleading. That's your rest mass. But if we wind up the mass, we also get the potential energy. So our effective mass, M effective, is just our total energy divided by the speed of light squared. So if we take this equation divided by c squared, we get the rest mass plus the potential energy divided by the speed of light squared. Now, that said, because we have added potential energy, it does technically weigh more, but you're dividing by c squared here, which is 3 times 10 to the 8th meters per second, or 9 times 10 to the 16th. So your potential energy here is like an astronomically small amount of your, like, it's barely there. But if you're working with something like protons, neutrons, electrons, their mass is like 10 to the negative 34. Because of that, these potential energy changes actually attribute a fair amount of mass to these molecules. The biggest example of this showed up when they were doing computer modeling, and they were modeling electron energies. And they were getting weird numbers for the energies of silver and mercury atoms. And what it worked out to be was that if you looked at just basic E equals mc squared, and you modeled these atoms, you found out that the 1s electrons in silver and mercury were moving faster than the speed of light based on their energies. So for something like silver or mercury, the electrons are moving so fast they're nearing relativistic speeds. So the electrons in the 1s electrons, the closest ones to the nucleus for silver and mercury, actually weigh a lot more than normal electrons. In fact, they're actually closer to the order of the protons and the neutrons that are in the nucleus. So if you look at the weight of mercury and silver, the isotopes don't even weigh what the numbers are because those electrons are actually raising up the mass of the atom. My live stream. So if we look at something like uranium-238, and the lie I told you was that this 238 here represents, well, this isn't the lie yet. There's 92 protons, and there's 146 neutrons. And the lie we teach you in Chem 1, and it is a lie by necessity, is that the weight of this atom is 238 AMUs, and we use that number. So why do we use that number? Well, the actual mass you would have to weigh. You can't figure out, because the reason why these protons and neutrons are coming together is that they lose energy, and that energy has associated mass with it. So the weight of a uranium-238 atom is actually less than 238. Iron actually is the most stable. If you count the number of protons and neutrons in iron and actually weigh an iron atom with those numbers of protons and neutrons, it weighs like a good 1 AMU less. So there's a substantial amount of energy loss. And if you want a good video about this, go look at PBS Spacetime, where they talk about the end of the universe. When the universe finally dies, it will be almost composed entirely of iron, because iron is the most stable nucleus on the periodic table. So over time, all the stars are going to convert everything to iron. Everything heavier than iron is going to slowly decay back to iron, and then we're just going to be left with a purely iron universe that decomposes into black holes, which eventually evaporate off. I don't know, Isaac. Shouldn't it technically get lighter? I mean, isn't like pain weakness leaving the body? Yeah, I used to bodybuild a lot. I'm about 30 pounds lighter than my peak weight. So I weigh 200 right now. At my peak bodybuilding, I was 230. At my peak power, I was 180 and benching 210. The bodybuilders are also the weakest lifters. They don't lift to get strong, they lift to get big and attractive. So if I wanted to do CrossFit and get like big and able to like bench press a quarter ton, I could have, but I didn't see a point to it. Most of the CrossFitters I saw, I just wasn't impressed with their physiques. They either looked like they were about to go beat up a tank, or they were just big, nasty muscle. Well, I mean, Isaac, so the reason I got into bodybuilding was, and I don't know if you've seen it, I've actually got a scar. Actually, kind of hard to see in this video. Yeah, you can kind of see it. There's a scar right there. So when I was in grad school, I clipped a steel pole on my bike and ended up breaking the bone in this arm. So when I went to grad school, I weighed 135 pounds. So I was like a scrawny guy. What I am now, minus 70 pounds. And so I had to go do physical therapy. And I was like, well, you got to do physical therapy. You might as well like go to the gym and get in really good shape. So I rehabbed my arm and then just started doing bench pressing, did the bodybuilding thing, and went from 135 to 175 in the course of like a year and a half. So yeah. Other thing, and this is something I dealt with bodybuilding culture, and I will admit to the bodybuilding culture, they are actually very nice people to deal with. Go for the body you want. I used to work out with a guy, he was huge into CrossFit. He was like, oh, I can like roll big tractor tires. And he would make fun of me because he's like, you're just going for a beach body. I was like, yes, that is 100% what I'm going for. I want to take off my shirt and look very impressive. And so being big and being able to bench a lot doesn't mean anything. It's just a matter of being happy with the way you look. Like, go work out. And my mentor for bodybuilding said, pick a goal and get there. And once you're there, don't go any further. Because there are some guys in the gym, they are big, nasty muscle, and they just think, I need to be bigger. And me, I was perfectly happy with the way I looked. So, but yeah, the bench press, don't worry about it. They're little guys. The guy I worked out with was a little guy, and it annoyed me because yeah, he could bench a lot more than his body weight because he wasn't that big. He also had these tiny arms, so he didn't have to go as far. If you got long arms like me, you got to push a long way for that bench press. And so yeah, he could bench 250 because he was only going like 6 inches. Sorry, a little bit annoyed with him. I mean, he was a big guy. Like, he was impressive, but watching him bench is like, yeah, I think you should have to go down 6 inches before you start talking to me about what I'm bench pressing. But I was also guilty of doing it to other guys in the gym too, so can't be that upset about it. Honestly, if you're looking for a form of working out that's really good for small guys or really thin guys, get into climbing. That's what I do. Weighing 150 is a godsend when you climb. I drag a lot of weight up the wall. Yeah, little guys who bench press are just generally hated. Because the other thing so the guy I worked out with, I called him Big Justin. He was built like a gorilla, but he was like those guys you see that are really buff on television. They're like 5'2", because somebody with my frame putting on 30 pounds of muscle mass looks impressive, but if you're like 5'2" and you put a whole bunch of muscle mass, you look bigger. And my frame can roughly carry 2 to 230. So this is, without steroids, this is as big as I'm getting. Yeah, get into climbing. Like, I envy the little guys. They're able to do super hard climbs because they don't weigh that much. Yeah, I got a hangboard so I can work out. I'm actually probably going to come back a stronger climber, stronger physically, not like stronger as good when I get back. But yeah, when I got my hangboard, it's actually for a grade higher than what I can actually climb, and it's the lowest grade you can buy. So I started on it, looked at a lot of the holds, and said those are just impossible holds. Now I'm actually doing some of the ones I thought were impossible, and actually getting some nice calluses on my hands now. So yeah, just stick with it. For me, working out is just kind of meditative time. I can really clear my mind when I work out. Doing about 4 days a week right now in quarantine. Heavy days one day, then a light day the next, and yeah. And again, just pick a goal, decide what you want to look like, and just go for that. Don't try to go further than that. A good video to watch about bodybuilding culture in general is called Bigger, Faster, Stronger. And I did appreciate the message. There was a guy, I vaguely remember him, but he got busted for steroids. And the guy just was big, ugly muscle. But he said the other thing to keep in mind when you work out is that particularly women are not attracted to big guys. And he said what he realized when he got big on steroids was that it wasn't women coming up to talk to him. It was a lot of men. They would push their girlfriends and was like, dude, you're so big and jacked. Just go for healthy looking. My personal opinion. Chemistry of bodybuilding. Don't take steroids would be my advice. It's low dose steroids don't do. Basically, if you're taking low dose steroids, and there are people who do that, particularly with Major League Baseball, they do take low dose steroids. You shouldn't need those to your 40s. Creatine is the only thing that is really useful for bodybuilding, and even then, creatine is more meant as you're going to do a power week, so you take creatine. So what creatine does is it converts ADP, adenosine diphosphate, into adenosine triphosphate ATP, which is what your cells use to power themselves. So when you take creatine, it helps with recovery. That said, your body maintains a certain level of creatine. So if you start taking it, your body will begin to produce less to compensate. But as far as the chemistry of bodybuilding, go take biology or kinesiology. But yeah, I'm not saying this use a PSA seriously. Don't do steroids and don't do half the supplements that are out there. A buddy of mine who was CrossFit, he took not steroids. Didn't take steroids. He took supplements, and he would say things like, "Man, I tried the supplement. It's great, but it feels like my skin's on fire." It's like 95% of supplements don't do anything. Creatine is the only one that really does something beneficial for your body, and even then, you only go on it and off it. For me, creatine was something I did before I went on break. So I would do 2 weeks of sheer power, working out twice a day, hard as you can, heaviest weights you can lift, creatine there to help with recovery, and then you took a week off, let your body relax, let your creatine go back to normal. But again, I was working out like 6 days a week too. Like, I'm not at that point in my life more. I have a life outside of working out now. It was different when the gym was at grad school and I could just like pop out and go to the gym and come back. Now I actually have to drive to the gym, so yeah, I'm not working out 6 days a week. If you want to get big, protein powder and do a protein blend. It's casein, whey, and I forget where the third one is. Best advice for protein supplement: do one before your workout and one after you work out. Now, that said, you're going to get big doing that. But the reason why you do it before, you do one serving before, is that it provides protein in your bloodstream for your muscles to recover during workout, and then you do protein afterwards. And what that will do is that it will basically supplement the protein in your bloodstream to help you after recovery. The more protein you take, the bigger you're going to get. That said, it also depends on lifts. So if you're doing a lot of powerlifting, like few repetitions, you're not going to get huge. If you do a lot of slow, light repetitions, so a lot of repetition work, you will get big. This was a mistake I made lifting one time, was that I did start getting really big and actually had to shave off the weight. So that's why I'm back down to 200, as I shave off that weight. But don't let people sell you on a whole bunch of supplements. Protein powder, I would recommend, even if you're just doing one dose when you work out, which is honestly sufficient. You want the protein for recovery. Otherwise, you're going to get anemia. And it's just because your body needs the protein. And if you're working out without the protein supplements, what you're going to end up doing is getting anemia because your body doesn't have enough protein. And again, I'd recommend a blended protein. You can work with whey or casein or the pure proteins. They're cheaper, but you need to reflect that in your diet as well. So if you're getting predominantly whey, which is milk protein, you need to get your proteins from other sources. like eggs. Eggs are a super cheap source of protein. And honestly, egg whites if you can. So like pull the yolk out and just have like the egg white. Super good for you. In terms of equipment for working out, I would say get the gloves. Um, the big thing being that like you will get like gnarly calluses on your hands if you don't wear the gloves. Gloves will keep your hands nice and soft. Hardbringer does a nice set, I think, for $40. Those things are indestructible, as far as I could tell. I think I would have to replace them once a year. But the Hardbringers and what they do is they wrap around your wrist. They take a lot of the weight off your fingers and put them into your wrist. You're not going to get away with like you're not going to be able to lift a lot when you do that, but it does help distribute the weight a lot more. Yeah, you're welcome. Well, see you next stream, Isaac. Any other questions? So it looks like there's pretty much just no one else left logged on. So thanks to all of y'all who could show up. Again, next week you should be in a nuclear, but honestly, we can just do review if you want next week. This is a kind of set your own pace kind of live stream. So till then, please keep up on the homeworks. Your final exam will be the week of finals. You will have from Monday at 12:01 a.m. up until Friday. Roughly 3:10 p.m. is when Blackboard is going to cut you off, but please take it earlier if you can. Big reason being is if you don't get the grade you want and you want to argue for points, I can't do that for you Friday afternoon because I had to get my grades in. But if you do it like Monday or Tuesday, there might be some room for discussion there. So again, we're going to try to keep this equitable. It's not like I'm saying, well, I won't talk to you at all. I'm going to try to keep your grades in consideration. But again, the more time you give me for that, the more time we're going to have to discuss. But if you take your exam at Friday at 3 o'clock in the afternoon, I have to submit my grades. I don't really have time to look through your grades to see if maybe there's somewhere to give your points back. So I will see you all Monday. Thanks for those of you who can show up, and yeah, see you next week.